Welcome to Maths with EJD. We're still talking about Laplace transform, which also plays into differential equations because basically Laplace transform is used to transform an expression in time domain into S domain, transforming differential equations into algebraic form for easier solving. But then sometimes when you're done solving such algebraic problems, you have an answer and you need to take it back into the time domain. And that is why it is important to talk about inverse Laplace transform. So as we delve into that, let's look at the definition and concept of inverse Laplace transform. So the inverse Laplace transform is the process of converting a function from the frequency domain or better still, complex plane represented by S, represented by small s, back into the time domain represented by t. So Laplace transform converts from time domain into frequency domain, and then inverse Laplace transforms back from uh, frequency domain to time domain. Okay, so the Laplace transform is widely used for analyzing systems in engineering and control theory. And inverse the inverse operation recovers the original time domain. So we are going back to where we came from, right? Recovers the original time domain function from its Laplace transform. Okay. Mathematically, the inverse Laplace transform is represented as f of t, back to the time domain is L inverse of fs. So that's how that is represented. So the question now is, what are the steps for that recovery? So steps to find the inverse. So first of all, you want to identify the Laplace transform. Which type is it based on all the things we had seen previously? Identify the Laplace transform. So given a function f of s we aim to find the corresponding time domain function. The corresponding time domain function f of t, just like we saw up there. Then number two, you can use inverse tables if available. Use inverse tables or your recognition, right, of possibilities. So a table of common, a table of common Laplace transforms, a table of common Laplace transforms is often used with lists known forms of L inverse of f of s. Okay. Number three, you can use different methods like partial fraction decomposition. Partial. Okay. Okay, let me talk about this and I'll elaborate on this later. Partial fraction decomposition. Interestingly, this is in the next video, I'll be focusing more on partial fraction decomposition to recover your time domain. So if fs is a rational function, okay, we might need to decompose. Might need to decompose it into simpler fractions, that can be inverted easily. So if you have rational functions, sometimes you don't know for sure how to take it back to the time domain. By the time you decompose using partial fractions, you can actually do that pretty much. So let's look at this simple example before I talk about methods for recovering the time domain for inverting a Laplace, for inverse, sure. So find the inverse Laplace transform of f of s, which is equal to 1 over s plus 2. Okay, so of course, as you can see, you can remember what we've been doing before and how to refer to it, or you can even use a table. So we can just say from standard tables, or from recognition. If you remember, right, this looks like when you have plus like this, it must have been coming from e raised power minus something, and that's minus 2, most likely. So from standard tables or from recognition, we know that that the L inverse of 1 over s plus a would have to be e raised power minus 80, generally speaking. Thus, uh, for a equals to, because the a now is equal to 2, because s plus 2, s plus a, so a is equals to, so for a equals to, the inverse is f of t, which is equal to e raised power minus 2t, easily. So that's how that goes. So as we round off, let's talk about um methods methods for inverse Laplace transform. So we've talked about one of the methods, definitely, and that is the partial fraction decomposition. Partial fraction decomposition. So if you have a rational function and you don't know what to do, how to get the inverse, You can decompose into partial fraction, and then from there you can easily recognize what you have. Another method is what is known as the convolution theorem. So you can use convolution theorem to find inverse. Convolution theorem. So that deals with the product of two functions, as we're going to see some videos down the line. And then we also have, lastly, the residue theorem. There may be other methods for sure, but in this series, I'll be looking at the partial fraction decomposition in the next video, followed by convolution theorem in another video, and then residue theorem in the last video under inverse Laplace. Okay, so with all this in place, let's take some practice questions based on what we have learned at least right now. And since I've also referred to a partial fraction decomposition, I might also give you something on partial fraction decomposition. So if you already know partial fraction, go ahead and do it. In fact, I think I treated partial fraction under uh, integration. So I think I took time to really explain. But of course, you can also wait for the next video where I'll be talking about partial fraction decomposition for inverse Laplace transform. So practice, find the inverse Laplace transform for the following. So one, you have f of s equals 1 over s squared plus 4. From the look of things, that should be sine. Okay, that should be sine uh 2t or something, or something like that. That should be sine 2t, I guess. I think it should be actually, because cos has s on top. Then number two, you have f of s equals 3 over s squared plus 6s plus 9. Now, this is hard to know just up front, so you may have to resolve into partial fraction. If you're able to do that, fine. If you're not, just watch out for the next video where I'll be taking care of that. So this is also in that same line. F of s equals 5s all over s squared plus 4s plus 5. So find the inverse Laplace transform of this three. Okay. So watch out for the next video. We'll be talking about partial fraction decomposition for inverse Laplace transform. So feel free to do this. Let me see in the comments either on YouTube or on Facebook. All right. Let me also know in the comments how helpful these videos are for you. And if you'd like me to teach a topic or solve a problem, I might be able to find time down the line to be able to answer you. Then of course, if you have not subscribed to this channel, you know you'll be missing a lot. In the next three videos, I'll be taking all these methods for finding inverse Laplace one after the other. So I'll start with partial fraction decomposition, and another video convolution theorem, another video residue theorem, which is related to complex analysis, right? And of course, for everyone, whether you have subscribed or you've subscribed before now, you just want to subscribe now, be sure to click the notification bell so you can always get alerted each time a new video is released. And don't forget to like and share this video widely among your circle of friends, because I have tons of videos here on different aspects of mathematics: set theory, calculus, matrices, name it, graph theory, network theory, probability, statistics, everything. I mean, almost everything you can think of. So, and the playlist keeps growing because I mean more ideas are coming. So share widely so that more people can have access to this great content, and so the videos can get recommended for more people that will need them. Okay, till I come your way again, keep doing maths right. Bye.